Hi, welcome to App Protector webinar. I'm Rino and I work on App Protector team at ASE. Today I'd like to talk about the role of integrity in the security of mobile applications. So first, let's understand what integrity is. Integrity is a property of data, and when this property is satisfied, we can be confident that the data in the system has not been accidentally altered, or altered without proper authorization. Some of the terms we often associate with integrity are authenticity, accuracy, and immutability. Integrity is also a part of the CIA triad, a core concept in cybersecurity that describes three fundamental principles of protecting information. Alongside integrity, it includes confidentiality and availability. Confidentiality ensures that the data in the system is accessible only to authorized users, and availability ensures that the data systems are accessible when needed. In today's presentation, we will focus only on integrity. To understand the importance of integrity in practice, let's consider the following example. Imagine that you have an important document that needs to be sent to your colleague. You package the document to an envelope and send it to your colleague. Your colleague receives the document and reads it. But how can you be sure that the document hasn't been altered by a third party during transit? In other terms, how can you be sure that the integrity of the document hasn't been compromised? As a solution to this problem, we can use hashing algorithms. Now, let's revisit the same example, but this time using hashing algorithms. We begin with the same document, but now, before packaging it to an envelope, we pass it to a hashing algorithm to get its hash. Once we get a hash, we store it to a secure location. Then we package the document to an envelope and send it to our colleague. On our colleague's end, once received, the document is passed to the same hashing algorithm to produce its hash. Before reading the document and trusting its content, our colleague calls us and we compare the hashes. If they match, the integrity is intact, and if they don't, it means that the document's integrity has been compromised. Of course, this is a simplified example, but it illustrates the core concept effectively. To be considered secure, hashing algorithms have to satisfy the following properties. The pre-image resistance states that once we have a hash, it has to be mathematically difficult to find the original plaintext. In other words, secure hashing algorithms are one-way functions. Collision resistance states that it has to be mathematically difficult to find two different messages that, when passed to the same hashing algorithm, produce the same hash. If such a pair of messages is found, it is said that a cryptographic hash collision has occurred, and the hashing algorithm can no longer be considered secure for use. Some famous hashing algorithms are, for example, MD5, SHA-1, SHA-2, especially in its 256-bit and 512-bit versions, and SHA-3. MD5 and SHA-1 are no longer secure because their collisions have been found, meaning that these functions should be avoided. However, SHA-2 and SHA-3 are still considered secure for use. Now, why is integrity important in the context of mobile applications? Well, integrity is crucial because attackers have a strong interest in compromising the integrity of your mobile apps. By successfully doing so, they can, for example, inject a malicious code or bypass security mechanisms implemented by the application's developer. And the attackers are typically motivated to perform those attacks by the pursuit of financial gain. One well-known example is the Spotify Premium hack, where attackers compromise the app's integrity to gain access to premium features without payment. Another similar example is the Pokemon Go app. This app was designed to encourage players to walk and explore the real world, benefiting their health while allowing them to collect points in the game. In this case, attackers managed to bypass the app's location tracking security mechanisms, enabling them to collect points without physically moving. And finally, there are fake apps, or clones, a type of attack that often affects banking applications. This type of attack usually begins with some form of phishing. The attackers can use automated calls, short messaging service, or emails to trick the victim into clicking on a malicious link. The victim is then further instructed to install the app that appears to be the real banking app, when in reality, it's a phishing app designed to steal user data. On iOS, this was usually done using progressive web applications, as they could be installed directly from the web browser. This allowed attackers to avoid using the official App Store. On Android, installing apps from the sources outside of the official App Store has always been possible. In 2020, the European Union proposed the Digital Markets Act, designed to ensure fair competition by imposing rules on large online platforms, known as the gatekeepers. In 2024, the Digital Markets Act fully came into effect, bringing changes to the way the iOS applications are distributed within the European Union. These new changes allow for the creation of alternative marketplaces and the distribution of apps on those marketplaces. Also, the developers are allowed to distribute the apps on their own websites. This means that now anyone who meets certain requirements can distribute the apps outside of the official App Store. Of course, this brings new possibilities for the legitimate businesses, but also simplifies the distribution of the malicious apps. So knowing all this, let's see what this process would look like from an attacker's perspective. The attacker would first clone a mobile application and modify its behavior, then distribute the modified app using their own website and trick the victim into installing it. Finally, after stealing the user's data, the attacker would use it for profit. If we are the owners of the app, this is definitely not a situation we want. What we want is to protect our product and users from such behavior. This can be achieved by finding a reliable security tool and implementing its protection mechanisms to make malicious modifications as difficult as possible. One of such security tools is Assay Integrity Check. Available for iOS and Android, Assay Integrity Check protects your app by detecting malicious modifications and provides a timely response mechanism to address attacks when detected. Implementing Integrity Check solution within your own app can be done in 4 simple steps. First, create the final version of your app, ready to be published on the App Store. Then you use the Integrity Check solution to calculate the app's footprint. You publish the app to the App Store, and finally, when users download and use your app, the mobile component of the solution will perform the runtime integrity checks. Now let's take a look at the demo of the solution for iOS mobile applications. On the left side, I have a simple demo app running on the real device. We can see that the app is trying to connect to the URL shown on the bottom of the screen. The app contains one image view and one label representing the status of the app's integrity. Right now, the integrity validation is failing because the mobile component is inactive. To activate the mobile component, we have to use the Integrity Check macOS tool. This will be shown in a few moments. On the right side of the screen, we have the project of the demo app, and we can see that the Assay Integrity SDK is embedded in the app. If we take a look at the app delegate, we can see that the SDK is being initialized with the license key. In the view controller, we can see that the validate integrity function is being called. If the signature validation passes successfully, we will see the check mark on the screen and the integrity status OK message will be shown. If the validation fails, the error will be shown on the screen, similar to the one we are seeing right now. Now let's say that this is the final version of the app that we want to publish on the App Store. Before publishing it, we have to activate the mobile component of the integrity check solution. Otherwise, the runtime integrity checks will always fail. To do so, let's first distribute the app and export the IPA file. For this demo, we will use the ad hoc distribution, but the process is the same when distributing for the App Store Connect. Select the provisioning profile and click Next. Now when the IPA file is exported, we can use the macOS Integrity Check tool to calculate the signature and activate the mobile component of the solution. Let's check if the code signing is set properly and press Continue. We save the changes and now we can try to install the app on our device. If we run the app, we can see that the mobile component is now active and the runtime validation of our app's integrity is successful. Now, in order to test the solution, we can try to make a malicious modification to the app. I will first create a new folder and copy the original app and the provisioning profile. I will then extract the app and open it in Hex Editor. In Hex Editor, I will make a simple modification. I will just replace the original URL that the app is using with a malicious one. The idea is to redirect the app's traffic to a malicious website. This again is a simplified example, and the attackers can make a more complex modifications to your app. But those modifications will be detected in the same way as the simple ones. Now let's save the change and package the app back to an IPA file. If we now try to install the modified IPA file, we won't be able to run the app. This happens because the app also protects the integrity of your apps based on the signature. And the modification caused the signature to change. Now at this point, the attacker has two options to make the app run. He can either re-sign the app with his own certificate and profile, or if he somehow gained the access to the original ones, he can use those. Typically, the attacker will re-sign the app using his own profile and successfully get a malicious clone of your app that can be run on mobile devices. For this demo, I will use the original profile. If I were to use a different profile, the only difference would be that I would need to change the bundle ID of the app, but everything else would remain the same. To re-sign the app, I will use a custom script and run it from terminal with the following command. The script creates the re-signed file and we can try to run it on a device. We can see that the app runs successfully and it's now trying to connect to the malicious link. But the good news is that the ASA integrity check has detected the modification. We can see that the integrity validation is failing because the app contains a modified segment. Of course, in the real app, you probably wouldn't want to show this information to the attacker. The good idea would be to crash the app or disable some core functionalities. However, if the user is using the unmodified app and the integrity validation is successful, there is no need for restrictions. Now, for Android apps, I'll invite my colleague Luca. Hi Luca, can you help me out with the Android part?
Of course, Rino, I've got the Android side covered. Hello, my name is Luca. I'm an Android developer in the App Protector team at ASA, and I'm going to show you how Integrity Check can help you protect your Android apps. The first step is to include Integrity Check in your project. Create a directory for plugin jar and a directory for SDK jar. Here it is placed in the app module. Now reference the plugin in the project level build Gradle file. Also, you need to set the path to the plugin jar in the plugin management in settings Gradle file. The plugin is referenced using the group ID and the file name. In the application module, apply the plugin under Plugins scope and add the SDK in the dependencies block, referencing the directory it's located in. To configure the plugin, use the integrity check block. Using the build type parameter, we set for the integrity check to only run on release builds. Using the license keys parameter, we set the license key for our application ID. I have created a delegate class for the integrity check SDK methods. It contains the integrity checker class instance, which we initialize using the application context, and the license key. And the only other method is the validate integrity method, which takes a callback interface as a parameter to report back the results, with it being either success or failure. In our view model, we initialize the SDK in the constructor of the view model. The validation method is called with the callback class that is used for updating the state of the application integrity. We observe the state from the main activity class. There we react according to the result of the integrity check. In this case, we only write out a success or failure message. This is the button that calls the integrity check validation. Here is the application. Now in the demo app, you can see the validate app integrity button, and when it's pressed, the validation is called and you can see the success message being shown on the application screen. Pay attention to the URL written below, as we are now going to try and change the URL. We are going to be mimicking an attacker trying to deceive the client using the application. Let's find our app and copy it to a separate directory where we can do some changes to it. Now, when this is copied, we use the APK tool, a popular decompilation tool, to unpack the application and decompile it into Smalley code. Now that we have the APK unpacked, we see that code obfuscation is used, so we need to do some more digging to find the URL we want to change. For this, we use another very popular decompilation tool, JDX. It decompiles the APK directly to Java when possible. We use its search function to find the URL. Now we read the package and class name it is located in. Now that we know where to look for, we go to the unpacked APK file and find the class of interest. Then we open it in a simple text editor, find the value of the URL and change it to anything we want. Now this is obviously not the correct URL. We save the file and use APK tool again to repackage the application. Next, we use zip align to align the APK as is required by the Android OS. All that is left is to sign the app using the APK signer tool. I'm using the default Android debug key store, but any key store would do. We now have our compromised app ready to install. But to do this, first we need to uninstall the original application because of the change key store, like so. Then we are going to install the tampered version and run it. We can see that the URL is changed. We validate the integrity and see that it is failed. In a few simple steps, we implemented the integrity check solution and help protect our app and our users from attackers. There you go, Reno. That about covers all of it.
Thank you, Luca. To wrap up this webinar, let's take a quick look at the upcoming features. In the next release, we will introduce the online integrity check. It will enhance security by validating your app signature with the secure backend server, and it will also allow you to track the integrity of your apps in real time on the App Protector portal. Of course, if you're interested in this solution or need any more details, feel free to contact us. Thanks for watching.